So the final type of bonding we need to look at is metallic bonding, and it's actually probably the simplest bonding type for you to learn off. So the clues in the name for this one, metallic bonding is to do with metals. So let's have a look at the metal, for example, sodium. Now for these sodium atoms, I've only drawn the outer shell electron. They're in group 1 and therefore they've got one electron in their outer shell. So in terms of what sodium wants to achieve, again it wants to get that full outer shell, and the easiest way it can do that is by losing that extra outer shell electron to go down to the previous shell. Now when we had ionic bonding, normally that would mean that the electron would go to a non-metal because they transfer electrons, but in this case metals by themselves do something a wee bit different. They're all individually going to lose that electron and kind of just hold on to it in between the different sodiums. What I mean by that is this. What we've now got is all of these sodium atoms have been turned into sodium ions. They're now sodium positive ions because they've all lost one electron. And what you notice is that the electrons haven't really gone anywhere. They're all stuck now between these ions. What we refer to these as is delocalized electrons. They don't really belong to any one sodium, but they're able to kind of move about in between the different sodium ions freely. The way we describe these sodium ions is that they're in a regular lattice or in regular layers. And in terms of how this bonding works, if you think about the two things we've got a negative charge on all these electrons that are able to move about. We've got a positive charge on all these different ions. So what we get is kind of like ionic bonding. We get an electrostatic attraction between the negatively charged electrons and the positively charged sodiums. So if you were asked to describe the structure of metallic bonding, which is just metallic structure, you would describe the fact you've got regular layers of positive ions and you've got delocalized electrons in between them. If you're asked to describe the bonding of a metallic structure, you'd be describing the electrostatic attraction between those layers of positive ions and the delocalized electrons. So once we got that picture, that is the same picture you're going to have to draw for every single metal. It doesn't actually change depending on the metal. You always will get these positive ions in layers, and you always will get electrons going in between them. So the last thing to look at is just some properties of this metallic structure. So we've got three properties we need to know and be able to explain. First thing is they've got high melting points and boiling points, so it takes a high temperature for them to melt. They're malleable and ductile, which are words you might recall. Malleable means you can hammer it into a shape, and ductile means being stretched into a wire. And the last thing is they're able to conduct electricity very well. So in terms of the high melting point, that again is to do with the strength of the attractions. Electrostatic attractions are very strong and hard to break, so it's going to take a lot of energy to break apart all the electrostatic attractions in this big structure and get it to melt into a liquid. So lots of energy is needed to break those strong electrostatic attractions. The second property is about malleable and ductile, which are more or less the same thing in terms of how you explain them. If we look back to our structure here, if we change the shape of this structure, so we start moving these ions down, the key thing is that this doesn't actually disrupt the bonding. Whenever you move these ions about and start changing their shape, the electrons, because they're delocalized, are able to move with the ions. So nothing gets broken, the electrons just come with the ions as they move, and we keep the metallic bonding intact. So the way we explain that is that the layers of ions are able to slide over each other without disrupting the bonding within that metallic structure. The last one is the fact that you're able to conduct electricity. As we talked about with ionic bonding, for something to conduct electricity, it needs to have a charge and needs to be able to move. The thing in the structure that has a charge and is able to move at all times is the delocalized electrons. They have a negative charge which can carry a current, and because they're able to move, because they're delocalized, they can very easily carry a current from one end to another. So delocalized electrons are able to move and carry charge. The last little thing about metals we need to know is a little kind of definition of a way we can mix metals together to make slightly better metals. That's known as making alloys. So the definition you have to learn off is this. An alloy is a mixture of two elements, at least one of which is a metal. Now in most cases that will be a mixture of two metals, but sometimes you can mix a metal and a non-metal together to make a slightly different property alloy. A couple of examples of that would be brass, which is a mixture of copper and zinc. So we mix those two metals together to get something with slightly better properties. Another example, which is an example of a metal with a non-metal, would be steel. Now steel is a mixture of mostly iron with a little bit of carbon mixed in to make it a little bit harder. So alloying two elements together is basically mixing them together, one of them is a metal, and it gives you metals with a better property.